is not as interactive as I would love to have it. I'd love to be sitting alongside you for the rest of a conference and take the opportunity given to me to share some information, then come back and discuss it with you in person. Today, though, we're going to do this as a webinar, and I sure appreciate the World Potato Congress for pulling this together, this webinar series. I invite you to continue to stay tuned into this series for other pertinent information for the potato industry around the world. And I also invite you to join in as the World Potato Congress joins in 2022, May 30th through the 2nd of June in Dublin. When I look at this picture, it's one of those pictures that just allows you to realize that there's some awesome stuff going on in the world every day, regardless of the stuff that we hear in the news or the things that might distract us. There's beauty like this on display every day, and we'll get to enjoy some of that as we talk potatoes in Ireland. But let's get into this presentation. Today we're going to talk a little bit about the climate and the impact that the changing climate might have on the removal of energy from a potato storage with ambient air ventilation system. So this is a ventilation system that uses outside air for cooling, as the majority of the ventilation systems around the globe do. This isn't a discussion about refrigerated potato storage, although we will mention refrigerated potato storage. My name's Todd Forbush. I work with Techmark Incorporated in Lansing, Michigan. Got my agricultural engineering degree from Michigan State University in 87 and a master's in 89, and put that to work trying to help potato growers every day around the U.S., around the state of Michigan, around the U.S., and around the world, store potatoes more effectively so that we can get that crop into the market to the people who need it. The outline of this presentation is going to follow a few simple steps. First, we're going to talk about the potato storage ventilation system as an energy conveyor. Then we're going to talk about how the air quality affects the capacity of that ventilation system. We'll then kind of turn the page and move on to climate change discussion and how the changing climate could impact the quality of the ambient air available for an ambient air cooled potato storage. We'll then shift gears back into potato storage ventilation, and we'll talk about the ventilation system's capacity to move energy and the potatoes' demand, the amount of energy that the crop is producing in the storage, and then we'll conclude. At the end of the discussion, we'll take questions. If you could post those in the Q&A, it's in the Zoom controls. The Q&A is the place for those questions. Sometimes folks will use the other tools available to them, the chat box or other things. For this presentation, we ask that you use the Q&A. Okay, so if you have questions as I go through the presentation, please feel free to enter them when the question comes up, but enter it in the Q&A. And then at the end of the presentation, we'll address those questions. Again, I want to thank the WPC for putting this together, and thank you all for coming for this opportunity to share with you. So again, the ventilation system in a potato storage, we're going to kind of shift gears and stop thinking about it as a fan and a humidifier and a duct and some other things to kind of get the air around. We're going to look at one of its real root uses. The ventilation system is the energy conveyor within the potato storage. It's one of its primary functions to move the energy from within the storage that's produced by the potatoes or infiltrates through the building, and to remove it so that that crop has a uniform environment, uniform temperature, uniform relative humidity, and proper carbon dioxide level to assure that we don't have issues with process quality as we store that crop. So I want to view the potato storage, and I'm going to move my picture here real quick. I think it might be over my slide. So I might move that around a little bit as we go. We want to view that potato storage ventilation system again as energy removal system. So I want to use an analogy that some of you might draw, or might be a better analogy for you, one of a grain elevator or bucket conveyor. So in a bucket conveyor, there are two things that determine how many metric tons of grain can be moved each hour. The first is the size of the buckets. That's going to impact the amount of grain that can be moved each hour. And in this analogy, that's going to kind of look like the air quality, the temperature of the air, the relative humidity of the air, and those things that impact the air quality. Then we talk about the speed that the conveyor moves. That will also impact the total amount of metric tons of grain that can be moved each hour with this bucket conveyor. That we're going to relate in this analogy to the air quantity, the amount of air we're using. And that would be like our CFM per hundredweight in North America, or CFM per ton in North America, or around the world in different units, but generally cubic meters per hour per metric ton. So this is the airflow rate. The speed of the belt is the airflow rate. The size of the buckets on the belt are about the quality of the air that we're moving. So in this analogy, we think of the bucket of outside air. If we just took a bucket load of outside air, we would define the quality of that air for a potato storage system as its capacity to remove energy from the storage environment. So the energy holding capacity of that bucket of air, okay, that volume of air, is going to be highly influenced by three different factors: its temperature, its water content, and the altitude that we're at as we're ventilating or using this outside air to remove energy from the potato storage. If we look at this energy conveyor and talk about some ways to get this job of moving energy done, we can get the energy movement job done using large buckets or high quality air and low volume or slow belt speed, low CFM per hundredweight, low cubic meters per hour per ton. Or we can move the same amount of energy with a smaller bucket, but more airflow, more cubic meters per hour per ton, more CFM per hundredweight. We can move the same amount of energy with both approaches. And it's important for us to remember that the potatoes set the demand, and the air system's capacity needs to match that demand. And we'll discuss that throughout the presentation. But how does the changing environment affect the potato storage ventilation? What does that have to do with potato storage ventilation? Well, as the environment changes, as environmental conditions change, they impact the ambient air quality. So we're going to have to study our current approach to ventilation using ambient air if the air quality is going to change the way the science currently predicts it to change. And we're going to talk about that science now and talk a little bit about how this climate change might impact ambient ventilation for potato storage going forward. So in 2018, a group from Michigan State University Department of Climatology got together with some in the academic realm, both in agriculture and the climate sciences, and partner with commercial folks. And I was very, very blessed to be one of those people that they contacted. Julie Winkler was the primary scientist on this work, and a reference to the work will be given at the end of the presentation. And we also have the paper and poster. A referee article was published, and this poster was generated with the results. And we're going to discuss those results. Now, in this part of the presentation, we'll talk about some climate change discussion. Now, remember, I'm the industry guy. I'm not the scientist. And so if you get too in depth on climate change discussion, I'm going to punt, okay? I'm going to defer. But the paper is available, the poster's available, and Julie Winkler would love to talk to you about potato storage and how the climate change might impact that potato storage. Also collaborators that you might be familiar with from Michigan State University, Dr. Dave Douches in the potato breeding department at Michigan State University, and Chris Long, the potato specialist, also assisting Potatoes USA. We're both collaborating on this work. So it was a very interesting group to be with. I will guarantee that to you for a guy that sits in industry 365 days of the year. It was interesting for me to step across into academia for a few hours a day, a couple times. So this study took place on the climate in Michigan. And you need to remember that the information that I'm sharing with you is based on climate projections in the state of Michigan in two different locations, Southwest Michigan, Eau Claire, and Central Michigan, Greenville. Why is it important in Michigan? Michigan's the largest producer of chipping potatoes in the United States. So chipping potatoes have a big impact on the economy in the state of Michigan. And so this study was funded by Project Green at Michigan State University as an important economic study for our economy here in the state of Michigan. So Dr. Winkler came up with a term called storage degree days, similar to your growing degree day model, where you would look at accumulation of heat above a base temperature. And in this study, we determined that we would break that or establish that base temperature based on storage conditions. So in the fall of the year, we use 12 degrees C as our wound healing and preconditioning temperature, and accumulated storage degree days anytime outside conditions were above 12 degrees C. During cool down, we cooled at 1/10 of a degree C per day to 8 degrees for our holding temperature. 8 degrees C is a typical holding temperature for potato chips here in the state of Michigan. And we held at 8 degrees C for the remainder of the storage season. Again, storage degree days were accumulated whenever the temperature is above the base. We then broke the storage season into 3 different time slices. The fall time slice, which was from September 15th through the beginning of a winter time slice. The winter time slice was variable based on climate projections. And the spring time slice was from when winter ended until June 30th. Now, how did that winter vary in length? And that's really what we're going to talk about is how much winter are we going to have? Well, we defined winter as 14 consecutive days that we didn't have over 0.25% change in storage degree days. So how does that play out in time? If the temperature is below 8 degrees C for 14 days in a row, winter started, okay? And then we marked that day that winter started, and we continued calling winter winter until we had 14 days where the accumulation of storage degree days exceeded 0.25% of the total for the year. Then we called it spring, okay? So really what we're gonna study is how long did we have acceptable cooling temperatures? How long was it that we didn't accumulate growing degree or storage degree days, excuse me. Just as a benchmark, a way to look at this, okay? We then broke up the historical time clock, if you will, into 4 different segments. There were 2 historical references studied. One, and I'll show some data on this, from 1960 to 2010. We wanted to get a feel for what had happened in the last, or in the 50 years preceding 2010, okay? We then looked at a historical reference for comparison purposes of a time slice in there that was a 30-year time slice from 1980 to 2010. And then we broke up the century that we're in and heading through right now into 3 different time slices. We're currently in early century, 2010 to 2030. We will move into mid-century, 2040 to 2060, and then late century from 2070 to 2090. Now, if you look at how gray my hair is and my age, you'll realize I'm not going to be here for all of those time slices. Okay, but I sat with my granddaughters last night. I've got two beautiful little granddaughters. They're twins, born on the 17th of September, just shortly after my birthday. And those little girls will be here. So it's very important for us to look at the future as we design buildings today that will last through this century. I always like to tell our team here at Techmark that we're designing buildings that will outlast us. And if we're going to do that, we need to look at what's going to happen in the future, not just what we're dealing with today. So this is the 1960 to 2010 comparison. And actually, there was a significant reduction in wintertime day length or days in that 50-day or 50-year slice from 2000 or 1960 to 2010. So changing climates are not new today. The climate changes all the time. And in the 50 years preceding 2010, we saw a substantial or a significant decrease in the length of winter. We're not going to talk about that today. However, the details are in the paper. What we are going to talk about today are those future time slices. So again, the next 70 years, it's projected that we could lose some cooling days in the wintertime for ambient cool potato storages. That means that the air quality, remember the start of our discussion about air quantity versus air quality in that ventilation system being an energy conveyor to remove energy from the storage, it requires good quality air. And in the next 50 to 70 years, we're going to see the air quality decrease. And we're representing that in this study by a decrease in the length of what we're calling winter for the study's purpose. What are some of the details of that decrease, if you will, or projected change in the length of winter in each of these time slices? Well, again, we used a reference of 1980 to 2020. So we use that 30-year time slice as a reference. Then we look at early century, and we looked at Eau Claire. Again, that's Southwest Michigan, a little warmer, okay? And Greenville, which is central Michigan. It's a cooler climate, okay? And that's where the two regions, really where the majority of chipping potatoes are produced and stored in the state of Michigan. Again, I want to stress, this is information specific to these weather stations. I don't want to project this information to a different region. Each region needs to stand on its own. But this is information that's used for this specific region here in the state of Michigan. So our early century, it's projected that we'll have anywhere from 8 to 10 fewer winter days than we had in the 1980 to 2010 reference. And in Greenville, 3 to 6 days fewer in that winter time frame. Mid-century, as we move into the 2040 to 2060 time slice, 14 to 20 days reduction in winter time for Eau Claire, and 11 to 17 days. You see fewer days lost in the northern growing region than the southern growing region. Amazing that those are just 2 hours or hour and 45 minutes apart. Eau Claire, however, is closer to Lake Michigan. It's going to have more of an impact of the lake. And Greenville is further away, less lake effect. And we all understand what a large body of water can do on the west side of a region. So this is, again, specific to Michigan. Late century, 2070 to 2090, in Eau Claire, the length of winter could drop by as many as 30 days. Interestingly, in Greenville, we also could drop by as many as 29 days. And these are different projections. We talk about this a little later, but I want to get this in now. There were actually 16 different global climate models used in this study, and there were 3 different gas generation rates. So this is quite a diverse study that Dr. Winkler put together. Really good science, way beyond me. Again, I'm just reporting this. I didn't author it. The potato storage side was my side. So The summary of the study from Michigan State is really that we need to pay attention to the quality of air that we have as we continue to use ambient air cooled potato storages. That's really the conclusion from that study. So, how does that average rise in temperature or reduction of wintertime, what does that mean for crop storage? Well, demand should stay pretty consistent. It may go up just slightly because demand, the amount of energy produced in a potato storage, is dependent on the crop in the storage, and that's going to stay pretty consistent. If we don't change our insulation values in storage, warmer or fewer winter days may end up having a little more infiltration. So we may need to modify the ventilation system slightly from a demand perspective. Performance perspective is really, or capacity perspective is really where we need to study. So we're going to talk a little bit now about some actual numbers to tie to that capacity based on ventilation rates and energy that needs to be moved. So those of you who know me, again, we're going to talk about demand, that is the potatoes' energy and the energy that comes in versus the capacity, the air system's ability to move energy. So those of you, again, that know me know I'm an engineer, so I love to put equations on the screen and talk about numbers. Okay, so here's Todd talking about numbers and equations again. This is the respiration equation. It's very important in potato storage. The potatoes continually taking a simple sugar, glucose, combining with 6 oxygens, and giving off carbon dioxide, water, and heat. So that's what the potatoes doing every day in storage. We can't stop it. We just have to understand it, okay? And that happens at varying levels based on the temperature of the crop and also the variety of the crop. Different varieties, different cultivars have different respiration rates at different temperatures. USDA numbers are real easy ones to work with. They're published, and of course, they're just suggestions. And again, a lot of this is based on suggestions. Specifics of your environment, specifics of your crop, cultivar are important to pay attention to when you're ventilating and storage. But really, as temperature cools down, what I wanted to show you is the respiration rate of potatoes drops. And from 20 degrees C down to 4 degrees C, we can have as much as a 5 times increase from the 4 to 5 degrees C potato storage to 20 degrees C, 4 to 5 times difference in the amount of energy that crop is producing. So that's why we cool potatoes down. And again, our model here, we'll talk about that 8 to 10 degrees C range because that's kind of where we hold the chip potatoes at. Now, another thing that we got to look at when we're talking about demand is the ability of the energy removal for cool down, right? As we cool that crop down from its harvest temperature to 8 degrees C, we have to have enough energy moving capacity to take that energy out of that crop. Potatoes are around 80% water, so picture it like cooling a swimming pool or heating a swimming pool. It doesn't happen quickly. It takes a lot of energy. So what I've got on this slide is the amount of energy required for cooling a crop at 3 different rates: 0.2 of a degree C a day, 0.6 of a degree C a day, and a degree C a day. So the center column shows the cooling required in watts per metric ton, and that ranges from 8.9 watts per metric ton for 0.2 up to 40 watts per metric ton for 1 degree C per day. And then the total watts per ton, so you'd add up the respiration rate and the cooling rate to get the total number of watts per ton that have to be removed. And at 10 degrees C, you can see the range from 35.7 to 65.2 watts per ton. That's how much energy this energy conveyor is going to have to haul for every ton of potatoes that are in that potato storage. That's the demand side of the equation. Now, if we look at the capacity side of the equation, there are really 3 factors in the capacity side of the equation. The first is how much time is the temperature outside cold enough to use for ambient air cooling. So time is a critical piece of this puzzle. The second is how big's that bucket? Is the air quality good, big buckets, or is the air quality diminished? Has it got a lot of humidity? Is it warm, smaller buckets? Okay, and then the third factor is how much air are we going to move? What's the ventilation rate? So those 3 factors, time, air quality, and ventilation rate, they really impact the capacity of that ventilation system to move energy. So what's going to happen to demand and capacity as outside average temperatures change, as these projections play out throughout the century? Well, demand may increase slightly, as I mentioned, because some infiltration if we don't have the building sealed up well enough. Also, the air we're bringing in for CO2 flushes will be lower quality air, will introduce more energy. So the demand may increase some, but demand is really not where the picture's at here. Capacity is really where the picture's at. So the capacity, as air quality diminishes, as warmer temperatures are coming on night times, that capacity is going to start to decrease as a result of having fewer hours, that time clock, fewer hours of ambient air available for cooling. So I want to step over into a little bit of a look at what's going on around the world right now, because we don't just store potatoes in the state of Michigan. They're stored all over the world. So as we look at different places around the world, I was fortunate to be a part as a student in 1985 of Engineering for Potatoes and a World Potato Symposium on potato storage. And I met some great individuals as I was a student from different parts of the world. And I've kept in contact with them. Many of them have passed now, which is sad, but true. And I will one day as well. But I had a chance to speak with many of them about their airflow rates that they use to ventilate a crop in their region. And as we look at these different regions, the reason I'm putting this on the screen is so that we can see as temperature at night changes, how ventilation rate recommended changes. So we see on the far left column is the region, and these are predominantly European, mainland Europe, and the US. So in mainland Europe, if you look in Paris, 10 degrees C minimum nighttime temperature. This is nighttime temperature during harvest time, okay? And then the recommended airflow rate, and I put it both in, for those of you who are using metric, I put that in cubic meters per hour per ton. And for those of us in the English system, I'm using CFM per hundredweight. Also, the temperatures are in both units just for ease of transfer. So if you look at France, the warmest nighttime temperatures, 50 degrees, airflow rates that range up to 150 cubic meters per ton per hour, or 4 cubic meters or CFM per hundredweight. As we move to cooler temperatures, as we're moving down, you'll notice that in the third and fourth columns, recommended ventilation rates also ratchet down. So we see this is kind of a playing out of climate change for storage without having to play it out over time. It plays it out in an instant of time over regions with the differences that we'll all experience because of our current local environment. This gives us some insight into what's going to happen in each of these regions as individual scientists evaluate how their region will change, what modifications they might have to make to their recommendations prior to those modifications being demanded by a change in outside air quality. So this is a slide that we're going to come back to in a few minutes. But again, the take home from this slide is quite basic. As outside temperature is warmer, the quality of that air is diminished, the quantity has to increase because the demand is constant. So what about this study, okay, and how it impacts ventilation system? Well, you know, it's going to be a reduction in the timepiece, right? There's going to be fewer hours of the day to ventilate. Well, that's the way it is today. If we look at that last chart I showed you, you know that in continental Europe, there are fewer hours of time to ambiently ventilate a potato storage than there are in the United States of America, just because of that large body of water that sits just to the west of continental Europe. So what about that energy carrying capacity of the ventilation system? Well, you know, I looked at an amount of energy that an air system has to move. And if we're going to look at keeping the temperature rise across the pile at 0.83 degrees C. That's 1.5 degrees Fahrenheit. So no more than 1.5 degrees temperature rise as that air moves through the potato pile. And this is in a bulk ventilated potato storage where the air moves from the bottom up. So as that air moves up, it's picking up energy, just as a bucket conveyor would pick up grain as it moves. And as it picks up that energy, it's going to increase in its temperature. We're going to hold down that temperature rise to 1.5 degrees Fahrenheit, which is a large temperature rise, by the way. But remember, the majority of that energy has to be moved for cooling, not for respiration. Okay, so this is a temperature rise that will occur during cooling, the maximum time needed. Okay, the maximum demand of the air system. So we're also going to cool at 0.2 degrees C, and we're doing that starting at 10 degrees C. So those are the parameters for this simple chart. And again, this is a snapshot of time. It changes as you move to different temperatures because of the amount of energy the air can hold. But I wanted to get us into one snapshot in time so we could get a feel for how things change. If we have 24 hours of ventilation in a daytime, so it's always below our holding temperature, always below 10 degrees C, we can always use that air to cool. In 24 hours, if we're going to move that amount of energy, we're going to have about 1.2 CFM per 100 weight, or about 45 cubic meters per ton per hour. Interestingly, that's about where our ventilation rates range when we're talking about the ideal condition of 24 hours available air. Now, on the left-hand column, you'll see that as the time is reduced, the amount of hours that we have to run that air system, to remove energy from the storage, the amount of energy that removed hasn't changed, so we have to increase the amount of air we're moving, the speed of that conveyor, the number of cubic meters per hour per ton, or CFM per 100 weight have to increase. And as the time comes down from 24 to 6 hours, it's an inverse rate, and you see that the ventilation rate has to increase fourfold as well as the time is decreased. It's the same amount of energy. You're either going to move it with high volumes of air in a short period of time, or you can do it with lower volumes of air in a long period of time if Mother Nature allows. If your climate doesn't allow, you have to have more air. Again, back to this slide, because this slide really brings home the point of trying to look at what the future might bring given the current circumstances across the globe with ambient air cooled potato storage. Again, warmer nighttime temperatures, higher ventilation rates, cooler nighttime temperatures, lower amount of air that has to be moved because of the number of hours available to get that job done. So conclusion, as the quality of the air changes in ambient air potato storages, we got a couple of things to look at. One of them is there's going to be more mechanical refrigeration used in potato storage. That's going to increase the cost of potato storage. And those of us who understand that this needs to be a sustainable business understand that as those costs increase, that's going to add costs to the overall system of producing potatoes. We have to be aware of that. Second is, if we're not going to increase the cooling, if we're in an area where we can use ambient storage and not need refrigeration, we're going to have to increase our airflow rates in order to get that job done. So those are the kind of the two ways that we can work to balance the capacity of the ventilation system, because if you throw refrigeration in to the system, you have a mechanical advantage. Now, the sizing of those refrigeration systems is probably going to have to ratchet upward from our basic that we're using today, because they're also going to have higher ambient, so higher condensing temperatures, and the capacity of the storage demand is going to be a little bit higher due to infiltration and bringing warm, high energy air in for CO2 control. The other option, again, added airflow capacity. Now, this is the actual title of the paper, Potential Impacts of Climate Change on Storage Conditions for Commercial Agriculture. An example for potato production in Michigan. Again, Dr. Winkler is the author of that paper, and all the climate change work in this presentation was pulled from that work by Dr. Winkler. The ventilation piece was information that we provided from here at TechMark. Again, you'll see some familiar names in the et al. Section, Dr. Douches, Chris Long, and some other scientists from Michigan State University. As we wrap up, I want to take this opportunity to thank the sponsors of the World Potato Congress, and I'll move my picture around just in case I'm blocking somebody. It's because these folks decide to invest in potatoes that each of us gets an opportunity to enjoy this today, cost-free, okay? And we get an opportunity to thank them by attending the World Potato Congress. So I want to put one last word in for the World Potato Congress. And I am going to now stop sharing my screen. Let me see if there's another slide. I don't think so. I'll stop sharing my screen and thank you for your time today. And now I'm going to look into the Q&A. Okay, so you're going to get me trying to figure this out. Okay, so and that's the chat. So I got to move on to the Q&A. Okay, no questions open. Okay, so here comes a question. Have scientists looked at potential impact of climate change on ambient relative humidity levels? What impact would that have on ventilation requirements? Great question. Again, I have to tell you that I'm not the climate change guy, okay? I would tell you that I heard a great presentation by Eric Snodgrass last week at Potato Expo. And that tuned me into some of the differences regionally that are occurring. And of course, to the point of this question, as relative humidities rise, the energy holding content of the air diminishes so that, you know, the ability to absorb more energy diminishes because the energy levels increase. So yeah, increased relative humidities will have a similar effect. So to answer the question, that's really where we're at. But as you say, we're going to have to take that over to the climate scientists and ask them to do that work. So the question now, what do you think about precipitation and climate change will have on the storage environment needs? Two sides, and actually in that work where we went and saw the ventilation rate in different areas, I was pretty convinced that harvest conditions played into the ventilation rate that a local area would recommend, right? I mean, local ventilation companies are going to design a ventilation system to meet demands. And the energy demand is the one we're talking about today, but water or drying out of a crop is another part of this potato storage ventilation system's job, you know? And so precipitation and increased relative humidity both would have a reduced drying effect with the ventilation system. Also might have more of an issue with the quality of the crop coming into the storage. And we are facing some of the warming trends we're talking about, but we're definitely facing some more, I would say, storms that impact, okay? And that presentation that Dr. Snodgrass did was very good when it came to talking about the impact of individual weather events on agriculture. And of course, if that precipitation referred to in the question took place during harvest, that's going to have a major impact on the quality of the crop going in and the amount of water that has to be handled in that system. Great question. Another question, what about energy electrical use in high ventilation rates versus low rates as we switch from one to the other solely for energy use? Well, I think that's a great question. And energy use is really, you know, it is something that we have taken for granted, more so in North America than in mainland Europe, because the rates for electricity here in North America are cheaper. That doesn't mean we need to be inefficient. The time to gain efficiency is when you have the latitude to gain efficiency. I think it's important for us to look at energy usage for potato storage. And those days of ventilating a potato storage for 24 hours because that's the way our dads and grandfathers had done it, I think those days need to be studied because really our idea of what a ventilation system needs to do versus what the crop needs is really pretty much being set up more by us than it is the crop. And if we pay attention to that crop, it'll speak to us in terms of what its needs are. And then we can study energy usage and try and get ahead of that curve before energy prices escalate or before we face this higher ventilation rate we need because of kind of smart ventilation versus ventilation that has to do with history. Do you see a big difference between varieties and ventilation rates? Do we see a big difference between varieties and ventilation rates? We see more of a difference between storage temperatures and ventilation rates. So the warmer you're going to hold a crop, the higher the respiration rate of the crop, the more the ventilation rate, higher the ventilation rate needs to be. So if a variety is being stored for processing, generally a higher ventilation rate. If a variety is being stored for seed or table, generally a lower ventilation rate. Those rates change, just as we discussed in the paper, because of the amount of energy that's being produced by those potatoes at different temperatures. So that's really the differences that we see for varieties, is more for use than specific varieties. But again, if you look at the respiration rate versus the amount of energy required for cooling, the respiration rate is a piece of the puzzle, but cooling is the larger piece of the puzzle in terms of total energy. Another question, changing air quality will affect potato storage production applications. So of course, ventilation and storage is the part that's not discussed very much. And that's why Dr. Winkler really took this on, because it is important to talk about the ventilation, the impact that climate change might have on ventilation design. Of course, that transfers over directly to potato production. And while I'm not on the production side, we do evaluate a lot of potatoes in our business for potato quality for processing. And we evaluate those potatoes pre-harvest to try and get a feel for how the environment, the agronomy, the variety, and the soil that was used impact the expression of the genetics of that crop to go into storage, because not every potato is created equally. And as those potatoes see more or see change in the climate during the production, it changes the quality of that potato coming into storage and how you should handle that potato in storage. So while storage is a separate part from production, it can only start with what was produced. It's a great question. It is important for us to remember that potatoes that have seen more heat during the growing season store differently than potatoes that haven't seen as much heat. And there's also periods that are stressful that might not be shown out in a growing degree day model that you have to pay attention to in terms of potatoes' ability to handle stress in storage. Great question. Thanks for that question. Next question. Great. So Nora's giving me the high sign, unless we've got other questions. Oh, one other question coming in. If we separately supply oxygen in stores to help increase shelf life of potatoes. Okay, so, I talked a little bit about bringing in outside air for CO2 flush. That has to do more with the carbon dioxide level than a decrease in oxygen level. And that's work that I was thankful to have a chance to do with some folks that deal with modified atmosphere storage at Michigan State when I was a graduate student. So it wasn't we kept the oxygen level high and let the CO2 level elevate and still had a problem. Okay, so the issue is we've got to get rid of the CO2. Oxygen alone is not going to solve the problem. Carbon dioxide elevation changes the way that CO2 diffuses through the tissue of the tuber, and you'll get a higher concentration of CO2 in the center of the tuber, which then can cause, in its extreme, black heart. Okay, so the CO2 becomes a poison. So it's a great question from the work that that I was fortunate to be a part of. Oxygen level not as critical to keep high as CO2 level is to keep down. If we have any other further questions, type them in the Q&A. If not, I just want to take again this time to thank you for taking the time to be with us today, to thank the World Potato Congress for putting together this series, and then also remind you to put it on your calendar. We're going to get together in Ireland. We're going to have some fun. We're going to talk potatoes, and it's going to be an awfully good time. So, yeah, I think we need to close it down. I'll get with any other questions that are coming in. Also, I wanted to tell you that if you wanted this presentation, this is going to be stored, available on demand by the World Potato Congress. And then also my contact information. I don't know how I can do this. I guess I can type it in the chat real quick. I'll type my contact information in the chat. And let me just do that. Chat. I'm not real good with this Zoom stuff, so have to bear with me here. Okay. If you need it, there's my contact information. Send me an email. Love to talk to you. And thanks everybody for joining today. Have an awesome day. Have a great January and February. I'll miss seeing you all at the conferences in North America this year. I'll miss that dearly. I can't wait until we can get back together. If you need anything specific, definitely reach out through email, through phone calls, and we'll get traveling as quick as we can again when it's safe. Be safe, everyone, and have a great, great winter and storage season. Bye for now.